Hey guys, in this video we're going to learn the basics of the vocabulary mostly of angular motion, which is to say rotation. I'm going to begin by defining all of the various vocabulary terms that we're going to use in this unit, and you can find this table on the first page in your notes packet. Now, the reason the table contains all of these things over here that you've already heard of, like displacement, velocity, etc., is because when we talk about things that are, say, rotating or spinning around, whatever it may be, there's a rotational analog for each of them, meaning there's a thing that happens in rotation which is analogous to the same thing that happens in linear terms. So, for example, if something is, say, moving forwards at some rate, right, a block, here it is, pew, right, moving forwards at some velocity, that's analogous to something, say, spinning around in a circle with, we'll learn to call it a certain angular velocity. You can understand the idea that, things can spin faster or slower when they are moving in circles, right? Just like things can be moving, faster or slower when they're moving in a straight line. We're not going to cover every single term in this table. This is just the table that you're going to fill out. Mostly we're going to introduce the basic vocabulary relating to displacement, velocity, acceleration, and also how we relate linear things to rotational things, such as in the case of something like a wheel, which is rolling along the ground and therefore both moving forwards and rotating at the same time. All right, so let's begin with units for things. Displacement, of course, is measured in units of meters. Hey, we knew that one. The rotational analog for displacement is called angular displacement. There's a bunch of these things where all you do is put the word angular in front of it, and all of a sudden it means for something that is moving in a circle. That says displacement, mumble, mumble. Okay. The symbol for angular displacement is delta theta. All right, now why does that make sense? Well, okay, so displacement, of course, is how far something goes. So in linear terms, right, if this block goes from here to here, it has undergone a certain linear displacement of delta x. For something which is rotating, be it a merry-go-round or a record player or whatever, right? If you're looking at a certain point on it, like say this one right here, and it is rotating around, right? In a certain amount of time, it might go through, I don't know, whatever this slice of a circle is. And that slice of a circle that it went through, you would call the angular displacement. So one possible unit for an angular displacement is degrees. Degrees are also the worst possible unit. No one actually uses them when we're doing something like rotational kinematics. It's just not done. Instead, we will use radians. Now, if you are unfamiliar with the unit of the radian from math class, a radian is related to the radius of the circle. 360 degrees is 2 pi radians. And what a radian is specifically is if you imagine you've got a circle and there's its radius right there. If you took that radius, that distance there, and you wrapped it around the edge of the circle, right, that same distance, that arc length is the radius of the circle, that distance that it would go around the circle would be 1 radian. Or rather, not the distance, but the number of degrees that it went around would be, instead of being measured in degrees, it would be 1 radian. It just so happens that it takes 2 pi radians to go all the way around the circle. So 2 radians gets you to like maybe there, 3 radians gets you to about here, and then there's this awkward little bit left over right there. If you figure out what this whole distance is in radians, it works out to be pi radians. Pi radians is halfway around a circle. So in other words, it takes about 3.14 radii to get halfway around a circle. The last unit that we will commonly use is the revolution. I'll just write rev in here. Obviously, 1 revolution is once all the way around a circle. So you could measure in degrees, I suppose. Radians are sort of the standard unit, but you'll see things like revolutions in the context of, like, say, revolutions per minute when they're talking about something like an angular velocity. All right, I suppose that brings us to our next one. Velocity, everybody knows, is measured in meters per second, while angular velocity is the rotational analog. The symbol for angular velocity is omega. Let me write that down here a little bigger. Omega. That's omega. It looks, I suppose, a little bit like a W. Don't call it a W. Whatever you do, it is not a W. And the reason I don't want you to call it a W is because whenever I am talking about quantities in physics, if I call it omega for angular velocity, and you are used to saying and thinking W, you won't know what I'm talking about. It's going to take you a minute to translate it, right, in your own brain because you've been thinking about it the wrong way. So right now, start thinking about it as being an omega. All right, that's what that symbol is. Mr. Erico, though, I thought this was an omega. Well, okay, Greek has upper and lowercase letters just like English. So this one, as in like I am the alpha and the omega, is a capital omega, whereas this one is a lowercase omega. Okay, angular velocity is measured in, typically we're going to say radians per second, right, which is analogous to meters per second. You might also see things like revolutions per minute, or RPMs. Radians per second, though, is the, let's call it the native unit, right? That's the one that everything is going to naturally come out in. All right, acceleration is in meters per second squared. All right, the rotational analog is, you guessed it, angular acceleration. And the symbol for that one is an alpha. Okay, again, that's a lowercase alpha. Alpha. Please do not call it Jesus fish. I have heard that one 1,000 times. And again, just like with omega, you're not being funny if you call it by the wrong name. You're just setting yourself up to be confused later on in the unit. If I'm saying alpha and you don't know what Greek letter that is, then you're in trouble. And you need to make sure, therefore, that you are constantly in the mental habit of thinking about alpha as alpha and not by any other pet name. All right, unsurprisingly, the units for it are radians per second squared. I have never seen it in any other units. Next up, though, is we need to talk about how you relate things like linear velocity and angular velocity. What I mean by that is the following. You can probably understand that, you know, if you've got a wheel, right, and the wheel is rolling along, right, it's got a linear velocity, but also it's, you know, rotating around at the same time. So it has an angular velocity as well, and there must be some relationship between those two quantities. So that's our next thing, is what is that relationship? Here you can see the three equations that are going to relate all the angular quantities we need to know about to the linear quantities we're going to need to know about. Okay, but what does R stand for, right? It's an R in each of these equations. Well, it's obviously radius. Everybody assumes that R means radius, and it's sort of radius, but actually it's distance from the pivot. All right, now, here's what I mean by that. The pivot is, let's say, at the center of this rotating object, which is maybe like a merry-go-round or something. If you've got one rider here who is at, I don't know, maybe 2 meters from the pivot, and then you've got another rider way out here who is 4 meters from the pivot. All riders on this merry-go-round are going to have the same angular velocity. All riders on this merry-go-round are going to go through the same angular displacement in a given amount of time, right? All the rotational quantities are going to be exactly the same. If the ride's speeding up or slowing down, for that matter, the alpha is going to be exactly the same for all of the riders. However, this guy out on the edge, since he's traveling through a greater distance than the guy who is closer in, is moving with a different linear speed. In fact, a greater linear speed because he has a greater distance from the pivot. If all riders have the same angular velocity, their linear velocity is based on their distance from the pivot. If you like, you could sort of relate this back to how fun the ride is. You guys know from experience that if you're the guy way out here on the edge, you are feeling the wind blowing through your hair, right? You are moving at a pretty high rate of speed, potentially. Whereas this guy closer into the middle is having a much more tame ride, and somebody standing actually directly on the pivot just goes around in a circle and doesn't really go anywhere. The reason for the difference between those three riders' experiences is, since they're standing at different distances from the pivot, their linear speeds are different, even though their angular speeds are exactly identical. Last thing we need to look at is the equations that you're going to use for rotational kinematics. So in other words, really just these first three equations that are in the second table on that front page. Rotational kinematics works exactly the same as linear kinematics, except we're using different letters because we're talking about different physical quantities. So if I were having you do this live in class, I would say, and now rewrite these using the analogous symbols. That's what I would like you to do, right, is rewrite them using rotational quantities instead of linear quantities to come up with the equations for rotational kinematics. So pause the video, rewrite them. If you're not sure what I mean by that, then you can maybe look at me translate the first one, and then you can go on and write the others. All right, so here's the first one. We said v is analogous to omega, right? Linear velocity is analogous to angular velocity. So that first equation would be omega equals omega naught plus, okay, not at, but alpha t. There's no such thing as rotational time. Time is just time. All right, if that made sense, then go ahead and try out the other two. All right, there we have it, the equations for rotational kinematics. So since we said it works exactly the same way, that means that you could be presented with a question where they are giving you something like, something starting from rest in a rotational sense, so angular velocity of 0. They could say it comes to like a final angular velocity of, I don't know, 4 radians per second, something like that. And then they would say something like it goes through 2 revolutions as it does this. Find the angular acceleration, or find the time that it takes for it to do this. Fine, you could probably see your way through plugging into the equations down below. The only caveat I've really got for you is the following. Well, maybe 2 things. So one would be, if you were paying attention a minute ago, we said revolutions is not okay. Kind of like how you can't just like plug in feet into our linear kinematics equations. Right? We said, no, sorry, got it. Everything's got to be in like meters and seconds. Okay, so no centimeters or anything. All right, well, revolutions is not okay. A revolution is 2 pi radians. So 2 revs would be 4 pi radians. And that could go in as delta theta into one or the other of these equations. The other caveat, though, that I've got is, what if they say something like it goes to a final linear speed of 4 meters per second? How are you supposed to do something like at the angular acceleration of like the tire or something like that? But you can always relate linear and angular using the equation like v equals omega r. V equals omega r or A equals alpha r are the ones that I would say we are most commonly going to use in order to convert between linear and angular. Things that you need to know. You need to know, summary of this video, what each of those Greek letters is called. You need to know what they represent. If you are not sure that you know what they're called and what they represent, then you should go back to the beginning of the video and sort of quickly skim your way through it and make sure that you understand. Or look back over the notes you took, make sure you know what it's saying. Also, you need to know how to convert between linear and angular things. If you can do all of that, then you learned everything that you needed to from this video.